A warm welcome to everyone joining us today for the 9th webinar of the webinar series of ReXtro 2025, the Silver Jubilee Tech Showcase of the Faculty of Engineering, University of Rome. We all live in a world built on structures, bridges, buildings, aircrafts, and countless engineering marvels, all working silently to support our daily lives. Yet, beneath their strength lies a delicate truth. Even the most powerful structures age, bend, and change over time. In an era where safety, precision, and reliability are critical, we need technologies that can see unseen, sensing the smallest cracks, the slightest shifts, and the earliest signs of damage. Today's session, innovative fiber optic sensors for structural health monitoring, invites us into a future where light itself becomes a tool for safeguarding the world around us, a future where structures can communicate their condition, where the engineers can detect problems long before failure, and where the engineers can detect problems long before their failure, and where safety becomes smarter, faster, and more proactive. I'm Janit Pushpanira, a third-year undergraduate at the Faculty of Engineering, University of Rome, and it's my pleasure to guide you through this session. Let's begin our journey into the future, a future where every structure can speak and every beam of light can help keep us safe. Every breakthrough begins with a curiosity, and every advancement in engineering begins with a visionary who dares to look deeper, beyond the surface, beyond the visible, into the hidden mechanics of the world around us. Today, we are honored to welcome such a visionary. Professor Gayan Kahandawa is an associate professor in Federation University, Australia, holding a PhD from the University of Southern Queensland, a BSc in Mechanical Engineering, and an MSc in Industrial Automation. His work bridges science and real-world impact, advancing how we understand, monitor, and safeguard engineering structures. Professor Kahandawa's research includes major collaboration with the Boeing Company on composite damage monitoring, a partnership that has led to 2 patents and over 20 high-impact publications. His expertise spans advanced composite structures, structural health monitoring, fiber optic sensing, and damage mechanics, supported by years of experience as a research fellow and an engineering educator. Sir, it's my privilege to welcome you to the ReXtro 2025 webinar night. Sir, the stage is yours.
Thank you, Janet. Thank you for the introduction. Good evening, everyone. So I will share my screen, and then we can start talking about fiber optics and structural monitoring. So let me know if you can see my screen. So can you see my screen? It's all good, is it?
Yes.
Okay, perfect. All right. So as Janet introduced, so I'm Gayan. I'm actually a associate professor in Federation University, Australia. Before that, I was actually graduated from University of Peradeniya, and have a master's in automation from University of Moratuara as well. And then did my PhD in University of Southern Queensland, as Janet mentioned. Okay. So moving forward, today I'm going to talk to you about the structural health monitoring using fiber optic sensors, which is actually my PhD research. And then from there, I have developed it for many other applications as well. So I will go through this research, and also to begin with, I would like to introduce the sensor itself for you. right? But to start with, I will start with my location where I am, and a little bit about the Federation University as well. So Federation University is in Victoria, in over here in Australia. It's actually southern tip of Australia, and we have three campuses: one in Ballarat, one in Gippsland, and in Berwick. So I am actually based in the Gippsland campus, but we work, across campus many times, right? So it's actually it really doesn't matter nowadays the location. So that's the situation we have after COVID, isn't it? So okay, so the university have a vision to develop a cooperative education model. That means all of our industry the degrees are industry connected. Our students are industry placed and they learn from the industry as well. So it's a little bit of a challenging model for the university, but it is actually giving us very good results. Our strength is in mostly in applied research, uh, particularly the engineering, AI, health, and regional development. And we are one of the highest graduate employability. We have one of the highest graduate employability in Australia for Federation University graduates. So we have strong relationship with industry, government, and then communities, and we are committed to innovation, regional growth, and student success. So some of these photos I have put up there. These are some of our campuses. You can see here, that's our very first campus, which is in Ballarat, over 150 years old. And we have campuses across across Victoria. All right, now to the topic. So the innovative fiber optic sensors for structural health monitoring. So this is actually very interesting topic. So I would like to introduce this technology to everyone. So if you are interested, you can dig more and then even use this technology for many applications. Okay. So to start with, I will introduce the fiber optic sensors, or we call it fiber backgrading sensors. Fiber backgrading sensor is physically, if you look at it, it's a optical fiber, right? If you are familiar with the communication industry where we use fiber for communication now, NBN, so that's looking very similar to that fiber, right? But there is a slight change in the material. In this fiber, we have a little bit of germanium. We call it germanium doped fibers. So the reason for that is I will explain why we need a little bit of germanium in it. But if I don't tell you, you will realize, okay, that looks like a normal fiber, right? So in this fiber, what we do is by using some radiation technique, we can create a grating in it, right? So I will explain a little bit more in my next slide. By creating this grating, what will happen is when we send light through the sensor or the fiber, because of the grating, part of the light will be reflected, right? So by looking at that reflected light, if you can understand the wavelength of the reflected light, we can actually get the idea about some physical properties closer to the sensor, right? In other words, if you have strained this sensor, that can be measured using the wavelength. Okay, so we call that particular wavelength Bragg wavelength, right? And then by looking at that, we should be able to identify strain in that particular sensing location. Okay, so the fiber itself, this is a cross section of the fiber. The core of the fiber, where actually the optical transmission happens, it is like 8 micrometers, very tiny, and there's a protective cladding 125 micrometer cladding around it. Okay, and then we can have more protective layers to protect the fiber, but typically when we attach these sensors, we try to remove these protective layers and then use it with the cladding only, right? So that way we can have efficient strain transfer from the surface attached to the fiber sensor itself. Okay, so to explain this, I will use this small animation video. So in here, as you can see, what we do is, this is the fiber, right? And then we use some UV radiation with a face mask. We call this a face mask, right? So it's like a mask we put on our face. We place it on top of the fiber, right? And then we radiate it. Because of the pattern in the face mask, right? So it will be writing a grating to the fiber, right? So that means in the fiber, uh, you will see that there will be a grating generated after we expose this to the UV radiation, right? So this is the grating we are talking about when we talk about fiber Bragg grating sensors, right? So this is very, very tiny, right? I mentioned that this one is 8 micrometers. So these are in nanometer range, right? Nanometer range. So then after creating the grating, so you will have a sensor now, right? So this is a sensor. So we can create our own sensors. So if we have the equipment, right? So based on the application, sometimes we will create our own sensors, or otherwise you can buy it from the suppliers as well, right? And in this grating, typically this grating length or the distance between these two gratings is in nanometer range, right? Most common wavelength is like 1500 nanometers, right? That's 1500 nanometers. Okay, so around that we can have a range, right? So it all depends on the equipment we have, sensitivity of the equipment. If our equipment is sensitive, then we can have a sensor in that sensitive range, right? Otherwise, the equipment may not read the sensor. Okay, so this is like more like now placing tiny mirrors inside the fiber, right? So it's just I'm trying to explain the theory, right? So it's like placing tiny mirrors. The distance between each mirror, right, is the grating length. Okay, so once we create this sensor, then if we pump broadband light through it, right, we send the light through it. Based on the grating length, part of that light will be reflected back, right? So as you can see here, we send the full spectrum, right? So all the wavelengths, and then part of that will be reflected, which is the light with the wavelength equal to the grating length. So we will see a tiny part of light coming back or reflected. If you observe the transmitted light from the other side, right, then you will see tiny part is missing, right? So in this case, if this one is 1550 nanometer range, you will see this wavelength as 1550 nanometers, right? So this is how we read the sensor, right? By observing the reflected light or the transmitted light. Now, if we subject the sensor to a strain, right, or you pull it, or you apply tension, right, tension to the sensor, you can see that it's straining now. So based on the strain, you will see these are moving now. The wavelength is increasing, right? So if I pull it, you will see that my wavelength is shifting into one direction, right? Because I am pulling the sensor. So this shift over here, right, from the original location of this sensor to the new location is actually equal to the real movement of the sensor. So this sensor provides us an absolute reading about the strain, right? So it's not converting anything because the light wavelength here, this is what we are measuring. So the wavelength shift is equal to the strain. Okay, so that's a direct advantage of this sensor. So if you compress the sensor, on the other hand, you will see the peak moving towards the other side, right? And if you heat it up again, it will move. So it can be used as a temperature sensor as well, right? So strain, temperature, and all of those sensors. Because that reflected light signal is a very, very thin signal, the advantage of that is we can have many, many gratings along the same fiber, right? So for an example, this one is 1540, this one is 1550, this one is 1560, this is 1570 and 1580. So we have 5 sensors on the same fiber. We don't have 2 fibers, so it's just one fiber, many sensors. So what will happen is now when you send the broadband light, we will see about 5 peaks actually reflecting, one from each sensor. So this is called multiplexing, right? So on the same fiber, we can have many sensors, right? So that's a big advantage of the fiber optic sensing, right? Just one fiber can have many sensors. But if you're using resistive strain gauges, you know that you have to wire them individually, right? Each resistive strain gauge has to be wired to the equipment individually, right? But here we can have one fiber uh, connecting many sensors to the equipment, right? So then each sensor can be used to measure different parameters. One is for pressure, one is for temperature, one is for acceleration, strain, and so on, right? So it can be used for measuring many things, right? So this is very useful when we want to measure, large structures, right? Many sensors can be used, but connected to the same equipment, right? So it multiplexing and multifunctional, and its long transmission distance. All of these are the advantages of sensor. I'm going to take one by one and explain. Okay. So yeah, so these sensors are widely used in structural health monitoring applications because of these advantages. Okay. All right. So if you try to understand these advantages a little bit more, multiplexing, as I explained, the same fiber can have many sensors, right? It can be dozens or hundreds. It actually limits, it's a limit of the equipment we use, not the sensor, right? If our equipment have a large range, sensitivity, then we can have many sensors. If our equipment is not that sensitive, is the sensitivity is in a small range, then it should be we can have like proportional number of sensors, right? So that's a big advantage of fiber optic sensors. It's immune to electromagnetic interferences because, as I explained, it sends light signal and returns light signal. Light signal is not going to be interfered by any electromagnetic interferences or radio frequency or any other thing, right? So because of that, this sensor can be installed in noisy environments. It can be inside the machine or in harsh environments in industrial or defense type of applications. It's not a problem because there is no interference from any other electromagnetic devices like motors or generators, transformers. Okay, so we can install the sensor even inside those equipment. It will only measure the strain and temperature. Okay, it's highly sensitive. That's the other big advantage. We are talking about nanometer level changes, right? So it's because of that, it's highly sensitive. So normally the strain gauges are typically working in micro strain level, right? But optical fibers can be, used to measure very tiny changes in the strain and temperature. Okay, and it's high resolution and it's repeatable, right? So same reading can be obtained many times because that is not going to be affected by other physical phenomena. Okay, it's lightweight and compact. As I told you, it's a very tiny sensor. It's like hair actually. If I drop it, sometimes it's hard to find it. Right? So it's very small, and because of that, it's very easy to attach, and use. Okay, and corrosion and chemical resistance is just glass, right? So as we know, it's not going to corrode, and there is no problem with moisture, or it's mostly, working with most of the chemicals as well. Okay, the glass is what we use for storing chemicals. Okay, high temperature tolerances. So there are special sensors which can take up to 800 degrees, so can be used in high temperature applications. Those sensors can be with some coatings to protect, right? So I've used copper coated sensors. I will show you that application later when we want to work in very high temperature applications, right? It can be used as a remote sensing sensor because, as we know, there is minimum loss in fiber when it transmitting the signal, right? So if you have the sensor 1 kilometer away, you can have your equipment here and you will read it. The idea of fiber optics is the zero loss, isn't it? So that's why we use it for communication industry. So same advantage here. So because this is fiber optics, it can be used to monitor sensors far away from the equipment, right? Which is not possible with resistive strain gauges, right? Because resistance of the cables. So all of those things are affecting the accuracies, but for fiber optics, that's not a problem. And it provides us absolute measurement, as I explained earlier. It actually measures the wavelength shift, which is directly proportional to the strain at the sensor point, right? So unlike strain gauges, what strain gauge does is, because of the elongation of the copper wires, the resistance is changing. So we measure the change of resistance, calculate the elongation based on equations, right? But here we actually measure the distance between the gratings, which is actually directly proportional to the strain at that point. Okay, so it's an absolute measurement. So we don't need to calibrate these sensors, right? So once you install it, if we can come back after a year and still you can measure it, right? Because we don't have to worry about shifting the wavelength because of other parameters rather than strain, right? So resistive strain gauges, over time, it is actually moving, isn't it? Because of moisture and then corrosion and because of many other reasons, resistance can change, right? So we cannot trust it. So we have to come and calibrate it again and then use it. Fiber optics, we don't need to do that, right? High bandwidth and fast response. So it's suitable for dynamic monitoring. So which is needed in some structural health monitoring applications. Because when we talk about structures, I will explain a little bit. It's not only the static structures we talk about machines as well, right? So sometimes we need dynamic measurements for those, so which is suitable for that. It's explosive resistant, that is any sparks, anything, because it's not electrical, it's all optical based sensing. Okay, durable sensor. It's minimum degradation of its glass, right? So if you protect the sensor physically, right? You mean somebody comes and pull it out, or someone damage it, then it will damage. It will last for a very long time. Okay, so I will show you some applications of that type of things we have done, and it can be easily integrated into smart materials, right? So that's also key factor of this sensor, because we can embed these sensors inside the material itself. Because it's so tiny, it's not going to affect the integrity of the material, right? So especially in materials such as composites, concrete, 3D printed structures, we can have the sensor inside the material itself, right? So that gives us many advantage. One is it's going to be safe inside, right? Number two, we are measuring strain inside the material, not on the surface, right? So in many applications, damage can start from inside, right? So if you have the sensors on the surface, maybe it's too late to detect it on the surface. If you can detect it closer to the damage, that would be more effective. So there are many advantages like that. Okay, so embedding is the one of the key advantages there, right? So if we cannot embed the strain gauges, because that strain gauge itself then will act like a damage, right? Because it's a piece of plastic, right? So we put it there, that's the damage then, right? Depending on the material as well. Okay, all right, so this is that comparison. That's the optical sensor over here, and that's the strain gauge. right? So when we embed it, these are some of the samples we created just to see how the sensor is settling in material. So here you can see that's a concrete surface here, and then this is a glass fiber surface here. So we have put the sensor in the interface, right? And you can see how it is sitting there, right? And this is actually inside the glass fiber reinforced composites. So that's the sensor sitting inside the material itself. Okay, so that's a big advantage to have that ability to embed the sensors. Okay, so because of that, this sensor is used in many applications, monitoring applications, in aircrafts, in defense applications, pipeline monitoring, oil and gas industry monitoring, bridges, like civil structures, right? So many applications. All right, so so when it comes to the structural monitoring, there are two parts. One is the sensor part. The other one is actually the monitoring or the intelligent part, smart part. Okay. So it is more like we are developing a nerve system for the structures, right? So we have our nerve system. If I have a problem in my elbow, I will feel it as a pain or something, then I know it's something's wrong with my elbow, right? Then I can go to a doctor and then do scans and find out what's wrong. So similar phenomena here. If an aircraft can feel about its structure, right? If something's wrong over here, if we can detect that, then we can fix that, right? So in most of the applications, because of not having this ability, we'll have to scan all the structure all the time, right? So aircrafts undergo monitoring operations time to time. You have to take it out of the operation and then using ultrasound or different techniques scan the structure for damages. That takes time, plus you are losing a lot of money because you have to take it out outside the operations, right? But if you can have a nerve system which can detect the damage itself, then we know and we have the confidence to fly the structure. We know that it's safe, right? And if something's wrong, it will recognize it, and then we can fix it early, right, before it getting worse. Okay, so this is actually the idea of monitoring. So now I'm going to talk about a couple of projects we use fiber optic sensors for monitoring. This is part of my PhD project with Boeing. And in that project, they wanted to monitor some of the aircraft structures and develop techniques to monitor those structures actively, right? So here you can see that's a cross section of a blade of an helicopter. So inside that one, they have something called torque tube, right? So that profile of the blade is to have that correct lift using the Bernoulli's theorem, but the integrity of that one is, or the force is actually mainly applied through this torque tube, right? So then this is the normal process when we want to do something like this. So what we do is, first thing we understand, okay, what is the part we want to monitor, right? And then we develop finite element models, and then by running the analysis, we will try to understand possible damage locations or stress concentrations, right? So if you realize, okay, there's a stress concentration over here, there's a possible stress concentration over there, then we try to put the sensors around that area, right? And then we create the samples and then we test it, right? So in these samples, we have the fiber optic sensors embedded. Similarly, to simulate a torque tube, you have created a sample and did the finite element modeling, and then put the sensors. Inside this, we have created damages as well. Like, in composites, there are few types of damages occurring frequently. One is called delamination. So these are laminated structures, right? So there can be debonding between the two laminates, right? So that's the defect. So to simulate that, we can create a delamination, and then we put the sensors to monitor that delamination, right? And we can advantage with the fiber optic sensor is we can put it very close to the delamination rather than putting it on the surface, right? And then we did some we had to build our own rig because we need to apply the similar type of forces on that. So and then we used the sensors to monitor it, right? By doing this at that time for surface attachment, fiber optic sensors was working really fine, no problems at all. It's providing us with very accurate readings. But when we start to embed the sensors, we realize that we have more challenges, right? So I'll show you what was happening. So even after embedding the sensors, we can see that the sensor spectrum is a little bit distorted, right? So we were looking at, normally we should get a very nice peak of the reflected light, but we started to see it is a little bit distorted now, right? As you can see here. And when we start to load it, that distortion is increasing, right? So that was an observation we found, and that was a challenge for us. In this case, as you can see, it's further distorting, but still we can find where the peak is, right? By calculating the distance between the peaks, we should be able to still estimate the strain there, right? In some cases that we found that it's actually, there are multiple peaks, multiple dominant peaks occurring. So in here you can see there are two peaks now. Which peak to consider? One is actually moved to the compression side, the other one is on the other side. So these type of challenges started to, we start to observe these type of things now. So that is where our research actually, we had to find new ways to deal with this type of sensors now. On the surface, no problem, it's working. But once you embed in composite materials, we start to get distorted sensor signals, right? So we decided to go with some processing techniques. We were looking at AI at that time, how to use AI to maybe help us to deal with these type of distortions, right? And then there was another challenge. We realized that if we want to feed this into AI is an algorithm run on a computer, right? So we have a light signal here. So we need to convert the light signal to uh, electrical signal now to record it, right? So if you convert this to electrical signal, whatever the reasons creating these distortions is going to vanish. We will end up with one voltage value, right? Because what we can do is we can send this to a photodiode or PD. That PD will generate one voltage, right? And then that voltage may not be meaning anything because we lost all the information in the spectrum itself. So that was another challenge. At that time, there were a couple of research groups in the world trying to solve this problem. So so we were in the same scenario. We couldn't find a way to go from here, right? And then by reading some other papers, we realized that, okay, if you can decode this signal into in a way, optically, we should be able to record that and then feed that into a neural network to understand the reasons or any physical properties we want to measure, right? So we decided to decode it optically and then use the decoded signal to train a neural network. So this is what decoding means. Over here, that's the original signal, right? And we send this signal through few more sensors. They are acting like filters, right? So that means this signal is fed through that another sensor, which can only reflect this wavelength, right? So part of the sensor will be reflected by this sensor, and some part of the sensor will be reflected by the second sensor and the third sensor likewise. So we can have array of filters to filter out the sensor signals, right? So I'll explain it with here. Now you can see what this is actually the optical circuit we have developed. The sensor, right? We send the light to the sensor, reflected light sent through another sensor, right? And that reflection sent through another sensor, and that reflection sent to another sensor. That's what actually we are talking about, decoding the signal. So each sensor will be reflecting different signal from the original sensor signal, right? And then each different filter signal fed into PDs separately. So we have, instead of one PD reading, now we ended up with multiple PD readings, photodiode readings, right? So that was used to train an ANN, or the artificial neural network, right? So the idea was, okay, we have our structure, healthy structure. While it's flying, we record these readings and we train our artificial neural network using that original healthy data, right? And then as soon as we introduce the damage to the structure, that pattern coming out of the PD is changed, right? Because the spectrum is distorting further, right? Which is very hard to find from our naked eye, because it's reading like a very irregular signal, right? We cannot see that the change from our naked eye, but the AI managed to detect that changing pattern based on the damage. So we managed to detect the damages with very high accuracy by using this technique. So this was a breakthrough for our research, and then ultimately this technology, all of this circuit and everything we did was patented. Because it was with Boeing, we had to patent it with the US Patent Office, and this patent was granted in 2013. So which is now Boeing is the only company can use this technology for monitoring. Okay, so that's one project. And then another project, we had a project with the Petronas, which is a Malaysian-based oil company. So they have pipelines, hundreds of kilometers of pipelines, and then with time, these aging pipelines are becoming, corroded, and then thinning the pipe, and they're becoming problematic for them. So for them, we have developed glass fiber wrapping to repair the fibers. And then on top of that, we started monitoring this wrapping to make sure that it is not going to fail, right? Because the bonding between the steel and the glass fiber, that's the location we wanted to monitor. And also because of the thinning, the fiber will load up with the pressure. So we wanted to make sure it is fit for the job. So similar to the previous application, finite element modeling, and then applying all the sensors, and then high pressure testing, all of those things, we managed to verify that the effectiveness of the uh, uh, damage repair. Okay, because without evaluating this type of technology, they cannot apply this right on the field. So they need evidence. So that is what fibers can do. And on top of that, each repair can be continuously monitored using the sensors embedded in the repair itself. We can use this with the concrete as well. So in this test, we have created this beam, concrete beam, and we have, for comparison, we have fiber optic sensors and the strain gauges here, but embedded inside on the rebar itself, we had fiber optic sensors, and then we were testing it, 4-point testing, to see whether we can monitor the failure with the optical sensors, right? So the fiber optic sensors can be easily used with concrete and monitor the rebar concrete interfaces, or for many applications. Okay, that is a commonly used technique nowadays. All right, so now we are going to talk about composite bridges. So in Australia, because we have many bridges in Australia, I don't know, maybe even in Queensland itself, we had how many, 10,000 bridges or so. So it's so much bridges. So maintaining bridges is a problem. So we was working on composite bridge girders, right? So these are glass fiber girders, and we have done a trial to demonstrate that it can be used for as a bridge building material. Normally we build bridge with concrete or steel, right? So fiber can be used as well. Early days we did with timber, so I'm going to come to that one as well. So in these beams, there were challenges when we use new material in engineering applications, because sometimes engineers doesn't trust these new materials, right? Especially when it comes to fiberglass, right? So civil engineers doesn't want structure to go and fail as a brittle failure. They want to see yielding, right? Yield and then fail. But glass fiber is as word indicates, they are brittle materials. It's glass, right? So the failure is brittle. So we need more confidence to use this material in civil applications, right? So that is where our next project actually leading to. So this project is with Department of Main Roads, uh, which is part of Queensland government. It's more like the RDA in Sri Lanka. Each state have different road authorities in Australia. So Department of Transport and Main Roads is the Queensland part of it. So this department had to monitor about 3,000 wooden bridges still serving in the road network, right? So because Australia is so large, original timber bridges still there, they're maintaining it. So replacing is take time, and we have to maintain those. So the key challenge they had at that time was when they have a damaged girder, timber girder, it was challenging for them to find a similar timber nowadays, right? Because the timber industry is now not as large as before, and they couldn't find correct timber, and they have 3,000 bridges to maintain. So they reached out, you know, to develop fiber composite girders to replace timber girders, right? So it's not replacing whole bridge; we are replacing one or two girders, right, as needed. And for that, we were designing fiber composite girders. Why fiber composite? There are a few reasons. One is if you use steel or concrete, they're too heavy, because these structures are not designed to take steel or concrete girders, right? If the girder is heavy, you have to replace the supports as well, which is expensive. Number two, we need to match the stiffness of the girders, the EI value of the girders, right? So if not, what will happen if timber girder placed with another girder, if the other girder is more stiff, timber will deform and all the load will be on that other girder, right? The new girder. If it is less stiff, it will deform and the timber will be loaded. So it has to have the same EI values. So the way we can do that is actually using fiber composites, because we can design the girder to have that particular EI value, right? So there are two designs. This one is called pull-through beams, and it's an I-beam section, and this is a rectangular section, and both designs actually were designed to match the EI value of timber. And the other problems now, so we have to test those. So we did destructive testing, shear testing, bending testing, all sort of testing. On top of that, we installed the optical sensors in the girder itself for monitoring. And because, as I mentioned, the failure of these girders are brittle failure, right? When we did the destructive testing, it was really bad. You know, it goes with a big bang and then it fails suddenly, right? So because they are glass composites, right? Yeah, so this is another project using optical fibers for monitoring the bridge girders. All right, so this project here is actually this Westgate Bridge is the main bridge in Melbourne. It connects the west side of Melbourne to the east side. It is the main bridge, I would say. Like without that, Melbourne cannot function. So it's an aging old bridge, very high, because the port is on the other side, right? The ships have to go through the bridge to get to the port, right? And this one, they had some issues, right? So because it's an aging bridge, there was some fatigue cracks starting in some joints, and then the Vic roads, which is the equivalent of RDA again. Vic road is the Victorian Road Authority. They reached out to us to see whether we develop a monitoring technique and evaluate the repairs they were planning to do to fix those problems. So again, so what we did, we go there and install optical sensors on that particular joint, right? As you can see here, this is somewhere here inside the bridge, and it's scary to see through these holes. It's like I don't know how far it is. It's very high. And then we install the sensors, right, in a way that we can monitor critical locations, right? As I told you, because we can multiplex the fiber optic sensors, we had sensors on the same fiber, right? So over here, this sensor is placed 4 millimeters from the weld line. The next one 6 millimeters away. So it's the same fiber. We wrote the fiber sensors to the fiber in a way that we have the spacing. So it's very easy to install after that, right? So we install it, and then we have mirrored it to have the redundancies and for the comparison reasons. And then excuse me, we monitored the joint for 2 weeks, even before the repair. We recorded the readings. We had about 12 sensors, right? And with the 100 hertz sampling rate, we were recording. The bridge is live, traffic is moving. It's very, very difficult to close this bridge. If you close this bridge, Melbourne stops, right? So it's a critical structure. So we need to make sure we are not disturbing the traffic flow. So it was all live when we did this, right? And then they did the repair, right? So they have did some crack repair and put some resin to fill the gaps, and that repair was conducted. We still keep on monitoring the location, and then we recorded for 2 more weeks after the repair as well, right? So now we ended up with huge data set, right, before and after. Because every sensor records 100 readings per second, and we have 12 sensors, 1 month worth of data, right? How do we compare? The other challenge we had was we don't know the load on top of us. If a truck moves across us, on top of us, it can be a 10-ton truck or a 40-ton truck. We don't know, right? So those load doesn't know. So what we did was we actually, by looking at the spikes recorded by the sensors, so each spike is like a high stress event, right? So we have actually used a technique called rain flow analysis, where we can put the high or the stress events into different buckets, so different intervals. And then in comparison, we found that after the repair, the high stress events has, number of events has decreased. It's about 20% decrease of high stress events after the repair. So that way we managed to provide the evidence needed for weak roads to make the decision to continue the repair. There are hundreds of joints over here, right? So we did that for one joint just to see whether the repair is effective, right? And then with that evidence, they managed to complete the repair. Okay, so that's another application. And the other advantage is these sensors are still there. This was done 10 years ago, right? So if we go now with the equipment, we connect the sensors to the equipment, we can read it again. We can compare the reading 10 years ago with today, because we don't need to calibrate it. Okay, so that's the advantage of fiber optic sensors. For very long time, we can use the same sensor for monitoring. We have to protect it physically. We have to cover it up, and then do not let anyone to damage this. If you save it physically, then the sensor will be safe, and we can use it for very, very long time. Okay. All right. So the next application of fiber optics here is actually for brake pads, right? So this is a company called Bendix. They are a brake pad manufacturer who is close to one of our campuses. So they're one of the largest in Australia. So they realized that with the increased number of electrical vehicles, their business is going is under threat, right? Because electrical vehicles, they mostly brake electrically and then use brake pads, comparatively less. So the brake pad wear is less. So that means most of the time, electric vehicles may not need to change their brake pads for the whole life of the vehicle, right? So so they realized that they wanted to develop smart brake pads now. It is one of, even though it is a little bit expensive than the normal brake pads, people will buy it if it is smart brake pads. So we have actually used optical fibers or the fiber brake rating sensors inside the brake pads, right? So in here, what we have done is we have embed the sensor in a way the with the wear, the sensor is wearing off as well, right? So unlike we normally do, normally what we do is we measure the shift of the uh, wavelength. But in this application, we're looking at the reduction of the peak of the sensor, right? So when the sensor is wearing off, right, the signal it can reflect is getting weaker and weaker. So signal is dying as well with the brake pad. So it's a sacrificer type of sensor. The sorry, the sensor actually wear off with the brake pad, and then we don't need to use expensive equipment to read this. You can use some PDs to read this. So this one actually you can see with the brake pad where the sensor signal dies as well. So that way we can monitor the remaining life of the brake pads. Meanwhile, by monitoring the wavelength shift, we should be able to monitor the temperature of the uh, brake pad itself, right? So what we have done is we embed the sensors, and then using a dynamo, we were loading and unloading the brake pads for hundreds of cycles to wear it off, and collected the data, and then managed to demonstrate that it can be used to monitor the brake pads, right? And then ultimately, this project is also ended up with a patent. This simple unit we have created can be used for monitoring the brake pads now. We don't need the expensive equipment. That is where the innovation is. We just need laser and a photodiode, right? And then everything else is through the AI-based system, which actually estimate the remaining life and the temperature and all of those. Okay, so this is a recent one. So that another application of fiber optic sensors. All right. So the last application I wanted to talk to you is, I think we are almost reaching our time. It's actually a current project. It just started. It is in the race car industry. So we are trying to use the fiber optic sensors for monitoring the car performance, right? So in racing industry, in each track, these vehicles suspension and everything is redesigned to suit the track, right? So to do that, they need to understand what sort of loads applying on the structure itself, right? So we are trying to use the optical sensors, right? And then while driving, we can record the stress values in that particular location they're interested of, right? And then change the suspension so that the forces are in their desirable range. Okay, most of the time at the moment what they do is they are heavily depend on modeling, like finite element analysis, and then also multi-body dynamics software. But now we are trying to use the optical sensors, right? Because it's very tiny and you can have it running there. And then nowadays we can have very tiny optical interrogators as well. So it can be there, and then some team members can monitor the strain values real time while the vehicle is on the track, right? And then they can optimize the vehicle's performance accordingly. So this project is just starting. We have not even done data collection yet. So that's a very new project using fiber optics So as you can see, the applications can be anywhere in the when you have these type of sensors. All right. Okay. So that's actually the lecture part of it. I'm happy to take any questions. If you have any questions, please. I'm happy to answer.
Thank you very much, sir, for that insightful and interesting eye-opening session on innovative fiber optics and sensors for the structural health monitoring. And now we invite our participants for submitting your questions. So Zoom Q&A panel is open. You can submit your questions.
Okay. Yeah. So they have to use the Q&A. Janet, is that what they have to? They cannot just unmute and talk, isn't it?
Yes. So we invite our participants to
Yeah,
share your
Charak got
questions.
his hands up.
Yes.
Okay.
Yes, so we have a question. How can fiber optic sensors be integrated with modern data analytics or AI tools?
Yeah. So so once we have connected the sensor to the interrogator or the unit we record it, so that after that it will become electrical signal, right? So that means after that it's like any other sensor, right? So then it can be used for we can use for any AI technique. So in most of those applications, we have used AI techniques. When we have a lot of data, it's much easier to use AI and train AI using the data. So after the interrogator, we call the equipment we have, which is used for reading the sensor. Then it's like a normal sensor. You can use it for any AI application. Yeah, yeah.
Yes, you can share if you have questions. There's another question, sir. What
Yeah.
challenges arise when installing fiber optic sensors in real structures?
Yeah, good question actually, because these fibers, without the protective coating, these fibers are brittle because they're glass, right? So we have to be very careful when we install the sensors, especially when we install this in concrete. We have to make sure that we are not going to break the sensor during the concrete pouring and the compression process, right? So that we have to be careful with that. But when the fiber is with the protective coating, it's very strong though. You can't break it actually, right? But then the problem is sensitivity of the sensor goes down because you have a sensor and you have a layer on top of it, right? And that means the sensitivity of the sensor goes down. It depends on the application. If it is all right, that's fine. Otherwise, you have to be careful, right? Very good question. I had these issues when I was doing it myself. I need to protect the sensors while I'm embedding it, right? So we need to be a little bit careful with that. Yeah, yeah.
So we have another question. What challenges arise when, I'm sorry, the same question. Thank you, sir.
Okay, yeah, yeah, yeah.
Yeah. Any questions? If you have, you can submit.
Yeah, there's one now here. Now I can, yeah. Okay, so all right. So this is how do we find the more practical, feasible projects, right? So good question. Again, I think when we want to do a good project, the key thing is, say, if you want to work with an industry, right? Uh, Key thing is not your expertise or what you can do and how good you are. That's not the main thing. It's actually what they want, right? So that you have to find out. If you can do something useful for the companies, right, they will give you the project, right? We have to demonstrate that by doing this, either they're going to save money, either they're going to improve their efficiencies, right, or to go for some new opportunities, right? These type of things are what companies are looking for, right? So I have seen this most of the time. What we do is we go and say how good I am, right? I'm a very good researcher, I can do this and that. So that's also needed, but for companies to give you projects, they need to see what is in it for them, right? If you can have some insight and see what type of problems they have, that's a very good chance you get that project, because you are solving their already existing problems, right? So that's one thing. The other thing is you can always collaborate, right? So if you can collaborate with uh, 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 more experienced people and then work on their projects, right? That wise also, that way also you can get good projects. Okay, does that answer the question?
And there's another question. Does partial reflection affects the data?
Yeah, okay. So partial reflection, the reason it doesn't affect actually, the reason is because we are not looking at the strength of the signal. We are looking at the wavelength, right? Even if you look at a partial signal, still we can, if we can identify the wavelength of the signal, then we are okay, right? Because we are looking at the wavelength shift, not these. If you are correct, when you divide the signal, actually it halves, right? One side get half of the energy, other side get the half of the energy. The strength of the signal actually half, but if you can measure the wavelength, that's all we need, right? So we can, if it is not, then we can still increase the laser power from one end, right? Then that way you can actually increase the partial signal strength as well, right? So it's a very good question, but we can deal with that. Yeah, yeah.
Thank you, sir. So I think we can conclude our Q&A session as well. So,
Yeah.
thank you, Professor Gayan Kahandawa, for sharing your expertise, your experience, your invaluable knowledge, and your remarkable vision with us today. Your insights into fiber optic sensing, structural health monitoring, and advanced composite technologies have opened our eyes. The future where engineering safety is smarter, more responsive, and guided by power of light. A heartfelt thank you to everyone who joined us today. Your curiosity, enthusiasm, and thoughtful engagement are what make ReXtro 2025 truly special. As we conclude today's session, let us carry forward a simple truth. Structures stand strong when we understand them, and the future becomes safer when we listen to what they reveal. Thank you, everyone who participated and contributed to this meaningful discussion. May today's insight